Where was I going with this? Okay, so push or pull an object, force. Okay. Newton. Does everyone remember Newton's first law? Anyone remember? Anyone know Newton's first law?
Any action has equal and opposite reaction.
No, that's his first. That's his third one. Okay. All right. Here's the deal. It's the idea that an object in motion will stay in motion, an object at rest will stay at rest. But let's define that a little clearer. Okay. If I have a ball and it's on a table, it's actually on the table, okay, and it's sitting still.
What's inside the ball?
Nothing. The ball's sitting still. How long was it going to stay sitting still?
Until something pushes or pulls it.
Okay, until something makes it move, right? Okay. If I have another ball and it's flying through space at a velocity 10 meters per second, and again it's flying through space like actual star space, like Star Wars space, okay? What is gonna make it change its velocity?
Another force acting on it.
Another force acting on it. We gotta have another force acting on it that will make it, so that will actually make it change velocity. Now, yes, friction, but there's no air, there's no anything at this point. But friction's an object. Okay. Here's the thing. Let's say I took this ball here. Okay. And now it's doing this. Velocity is what kind of thing? Velocity is what kind of thing? Distance and a direction, or not distance and direction, a speed or a magnitude and a direction, right? Velocity is a magnitude and direction. It's what kind of thing? A vector, right? It's a vector. So let me ask you a question. I have a ball here, velocity 10 meters a second, ball here going a different direction, velocity 10 meters a second. Have I changed velocities?
Yeah.
Why?
Because velocity is magnitude and direction.
I changed direction. Up until now, we've been talking about velocity in one axis, right? So we're talking about the velocity. We've always been changing the velocity in the one. We've just been changing the magnitude, right? It's got 10 meters a second, then it goes up 5 meters a second, or something to that effect, right? We've been just playing with the magnitude. But you can change the direction. And changing the direction means that you are, in fact, changing the velocity. Okay? And you're doing that instantaneously? Not necessarily. It's got to take a certain amount of what? Time. Okay? And what does that equal? Acceleration. So if I change my velocity in a certain amount of time, I have created an acceleration. Okay? But again, because of this first law, how did this thing move? How did I change direction? What caused the thing to change direction? Some sort of force that acted upon it. So I have a force is equal to my mass
Times its acceleration.
times acceleration. Okay? Now, I'm going to get to that in a second. That's actually, that F equals ma is the second law. We'll talk a little bit more about that in a minute. But here's another point. Let's talk about this changing direction, acceleration, and force. By swinging the ball
I'm
up.
so nervous. This is going to be really actually, try it on your
If that gets my knee, I
Please
swear
don't.
to God.
It really actually is very bothersome.
So I'm swinging. The longer you talk, the longer I'm swinging this. Let me get to this, okay? I'm swinging the ball around. The velocity, the speed that it has, is it changing? It's relatively constant speed, right? But what is changing? The direction. So do I have an acceleration?
No.
Yes. If I'm changing direction, the speed is not changing.
Negative to positive.
What do you mean negative? Well, the direction is going around in a circle. It's changing tangential direction, right? If I'm taking an object, if I'm taking an object, all right, and I swing it like this, I have a velocity here, tangential velocity. You guys see that? Okay. So as time goes on, my direction is changing, even though my speed is not. So if my direction is changing, even if my speed is not, what is changing? My what?
Your velocity.
My velocity. And if my velocity is changing in a certain amount of time, what do I have? I have an acceleration. So I do have acceleration. And what I have is centripetal acceleration. That's centripetal.
That keeps getting dangerously close to you.
He's right, you don't.
Wait, I'm not done yet.
It's still
I'm not gonna feel bad for you when it hits you on the
This
head.
puts us in danger.
Stop, quiet. So now, okay, but what is the force? So if I have an acceleration, what must I be doing to the ball? What must I be applying to it? Force. Where's the force coming from? Directly on the ball. The force directly on the ball is coming from the string, and then from my hand. Okay, so the string is pulling that ball in. We'll deal with this specific example when we get to centripetal force very shortly.
Is that what those flying cows in the surprises room?
Yes. And he talks about angular momentum as well. All right. So here's a scenario. Okay? The first law, Newton's first law, is this: that an object. Let's be very clear. An object at rest will stay at rest. An object with a velocity sorry, I can't tell between my L's and my C's anymore. An object with a velocity will stay at that velocity until what?
Until acted upon by an outside force.
So acted upon by a force. Now look, let's be very clear. You're going to hear object at rest will stay at rest, object in motion will stay in motion. It's not just motion and rest, it's velocity. Because it's not just that I am in motion, it's my direction of motion. In addition, this sentence is redundant. Why is this sentence redundant?
Because it has a velocity of 0, it still has a velocity of 0.
Correct. If I'm at rest, my velocity is 0. Really, the law should just be this.
Yeah, but Newton didn't know that. How'd you make him slack?
He was trying to explain it so everyone would understand it. He knows this, or knew this when he was one. So this is the deal. Okay? It's redundant. An object with a specific velocity will stay at that velocity, whether it's at 0 or not, until it's acted upon by an outside force. Make sense? Good? Okay. Newton's second law. Okay? In order to make that object accelerate, okay, I have to apply a force to it to make that accelerate. Now, acceleration is what kind of thing? Basic thing. A, because of the V, vector, right? Okay? Mass. What is mass?
Well, it's not weight.
The force of gravity.
Mass. What is mass?
How much gravity affects the object?
Not necessarily. The amount of stuff I have, the amount of matter. Not the density of the thing, not how much space the matter takes up, but the amount of matter that I have. Okay? That's matter. Now, does matter have direction?
Does matter matter?
Does matter have direction?
No.
No. So is mass a vector?
No.
No, it's not. But my acceleration is, isn't it? I can either be accelerating up or down or left or right, right? So if I have a scalar times a vector, what must my force be? A vector. If I have a scalar times a vector, it's like it's because this is still a scalar and a direction, right? Scalar, direction, right? So because I have a direction, this makes logical sense because if I'm going to push an object, it's going to accelerate in the direction I'm pushing, right? In order for it to accelerate in a specific direction, I have to have a force going in that direction. So the force gets its direction from acceleration, or the acceleration gets its direction from the force, but they're the same direction. Does that make sense? Everyone clear with that? So these have directions. It's important because we're going to be dealing with that. Again, remember I talked about how vectors are going to be our basis for a little while. Okay, so if you don't get vectors, you better come see me. Okay, let's talk about the units. What's the unit for acceleration?
Meters per second squared.
Okay, meters per second squared, or I like to say at the beginning of things, meters per second, right? What's the unit for mass?
Grams.
Grams. In this case, we're going to use kilograms. Kilograms. And then what's the basic unit for force? Newtons. Okay? This means, let's talk about this. I know a lot of you guys want to memorize the equation. I know it seems like I'm being redundant and slow. I'm doing it purposefully because I want to go over what this means. I want you to really understand the equation. Don't just memorize F equals ma. Great, everyone can memorize that.
Or F equals AN.
That's fine. But let's understand what this means. It means, what it means is it will take 1 Newton of force to take 1 kilogram of mass and change its velocity 1 meter per second every second. I'm going to say that again. It takes 1 Newton of force to take 1 kilogram of mass and change its velocity by 1 meter a second in 1 second time. Deja vu? Uh-oh. Okay. Does that make sense? Okay. And I'm breaking it down like that because I want you to realize what's really happening. So if I take an object, now look, in this case it's positive, but could I have a negative change in my velocity? Well, that would mean I'd have to, what kind of force? Negative force, right? I can have a positive change in my velocity, gives me a positive force. A negative change in my velocity, a negative force. Can I have negative mass? No. Not in practical physics, okay? All right. We're not going to do practical. That's what college is for. Theoretical physics. There you go. All right. So we really can't have a negative mass. So we've got this. Now, so for example, if I had 2 kilograms of mass and I wanted to change its velocity by 6 meters a second in 2 seconds, how much force would I need?
6 meters per second over 2 is 3. What was the first thing?
2 kilograms.
2 kilograms times what was the second thing?
2 kilograms of mass, changing it 6 meters a second. It's a change in velocity
4.
over 2 seconds.
No.
Well,
No. 6 newtons.
6 newtons. 2 kilograms of mass. Okay, I'm going to change it by 6 meters per second. I just want everyone to realize that Matt and Sam, or Thomas, are gone. Thomas and Matt are gone, and how quiet it is. Sorry, I know.
Why are we noticing that?
Because it's really quiet.
Do you want to like time it or something, Mr. C?
Huh?
So I don't really know your name, Mr. C.
I know, right.
Mr. A.
Mr. Z.
Recorded. That's recorded. That's really mean. That's really mean. I'm going to email this to both of your parents and have them actually watch it. So 6 meters a second divided by 2 seconds is what? 3 meters per second squared times 2, which is 6 newtons. No one answered me correctly except for one she did, so I'm just going through it.
Do things.
Okay, now that I answered you correctly, can I do a quick story?
No, I've got to move forward. Well, tell me later.
I called her window chat. She laughed.
Okay. Okay. So we're clear on this. Yes? Okay. Does anyone know Newton's third law?
Every action has an equal and opposite reaction.
Wait, what was second law? Did we skip that one? Or was that another one?
Second law is this. This is the second law.
That's always confused me. It's not really a law, it's an equation.
Okay. That's why I just spent the last 10 minutes or 5 minutes doing this conversation.
Yeah, but I don't know.
I'm trying to explain what it is. Because you keep focusing on this. Don't focus on this. Focus on what we were talking about. It's the idea that to accelerate a kilogram of mass, 1 meter per second squared, it takes 1 Newton of force. That's all it is. It's an equation, but it's more than an equation. Okay? All right. It's a relationship. It's like a relationship. Okay. The Newton's third law, you said what? What'd you say?
For every action is an equal or opposite.
Okay. So for every action, and I'm going to call it this way, for every force, there is an equal and what?
Opposite. Force.
Force. Okay? All right. So, here's the deal. Let's talk about what this means. Because there's some nuances here. I want to make sure we understand. Nuance. Okay. Pardon me. Okay. All right. Now, I need a pencil. I need some space. Okay. All right. Now, here's the thing. So let's talk about weight for 1 second, guys. Weight. What is weight?
It's the
How heavy is it?
force you put.
It's the effect of gravity on your what? On your mass. Okay. If you're here, gravity pulls on you at what rate?
9.9
meters per second squared. Is that the same rate of pull on the moon? No. Okay. But does your mass change if you were going to be here or the moon?
Yeah.
No. The mass doesn't change. If your acceleration changes, if your acceleration changes and your mass does not, your force due to gravity or your weight must change. Does that make sense? Okay. So your weight is a force due to gravity. This pencil weighs about maybe a quarter of a Newton or something, right?
And what?
Quarter of a Newton. Newton's a force.
Oh,
Weight is a force. Weight is a force.
that's weird.
I know, that's why I'm trying to deal with these nuances, right?
I thought the unit for weight was no, like that's the
Serious?
Yeah, I know, back in England, right?
We're modern now.
No, it's a million units. It's a million, there's grams.
They still use some.
We
They
move
still
on
use
from
them.
modern times.
They
That
still
is
use them.
what? That's an actual, right. So I've got, if I let this pencil go, what's going to happen to it, guys? It's going to fall, right? So right now, what's it doing? Is it falling? Okay. What's its motion? Nothing. So its acceleration is what? So if its acceleration is 0, what's the force on it? The net force on it is what? 0. The net force is 0, guys. It's not. Net force is 0. Is the force of gravity still acting on this? But what else is acting on it?
Your hand
The force of my hand. So how much force am I holding up the pencil with?
9.82 meters per
Not
second.
negative. No, I said this is a quarter Newton. Quarter Newton of force. It's a quarter Newton of weight. I'm holding it up with a quarter Newton of force.
You're so strong.
I know. Right? So I place the pencil on the table. Is the pencil moving vertically? No. So how much force must the table be applying to the pencil?
Quarter Newton.
If it was applying more, what would happen to it?
Head would start
If
up.
I apply more force than quarter Newton, it would be accelerating up. Okay? Alright, now, the table's applying quarter Newton. Ready? Shh. Does everyone agree with me that this 9-ball beer ball weighs more, has more weight and more mass than the pencil?
I would agree.
Okay? Let's say it's about 1.5 Newtons. I put this 9-ball on the table. How much force is the table pushing back the 9-ball? 1.5 Newtons. So first it was pushing back at 1/4 Newton. Now it's pushing back at 1.5 Newtons. Okay? Now the table's pushing back at 100 Newtons.
You got in trouble for doing that.
Too late.
Don't do it again.
Okay. It's about 100 Newtons, right? Okay? If that weighs 100 Newtons, how much is the table pushing back? 100 Newtons. So okay. I think I know where you're going. I'm going to hold 1/4 Newton. I'm going to hold 1.5 Newtons. I'm going to hold 100 Newtons. Okay? Wait a minute. Did you see me have to do something? I have to use my brain to do that, right?
Maybe.
Right? Does the table have a brain?
Yeah.
Then how does it know
Yahweh
what
is
to
in
push
it.
back on?
That's how the universe works, dog.
But
Yeah.
it is your question. Wait. This is important. This is an important nuance, guys. This is an important nuance.
It's a solid.
It doesn't know, but it must know because it's doing
It's
obviously.
solid, not right. It's
But it has to be. It's got to.
It must be solid.
If it's a it must be. Listen, guys. This is important. This is important. I had a buddy of mine who you guys know the therm, you know what a thermos is, right?
No, I have no idea.
I'm not sitting on it, so.
So his point was he said he keeps the hot things hot, the cold things cold. How do it know, right? How does it know?
Your friend sounds like a
How does the table know? How does the table know how much to push back? Let's talk about this.
Oh,
I'm
I
gonna
know.
show you.
It has a capacity, and anything beneath that capacity it can hold.
Yeah, but it's still pushing. It's actively pushing back. So you're pushing the ball.
But for
So
a standing object,
That
it's
force
not.
is transferred into the floor from the pegboard.
well, yeah, but so the floor must also know. But the floor must then also know how much to push back.
Yes.
Okay, hold on. Here we go.
This makes my
I'm gonna guys, quiet. Okay, I'm not gonna drop the ball. I take.
Don't drop the ball, Mr. A.
I will not stop having fun. Here's my pencil. Watch. I'm gonna put the pencil not on the table but on the ruler. Actually, it's your pencil.
Physics.
Okay. So at this point, if the pencil weighs 1/4 Newton, how much force is the ruler pushing back on the pencil?
1/4 Newton.
Yeah.
Quarter Newton.
Now, if the ball weighs 1.5 Newtons, how much is the ruler pushing back?
Newton and a half.
Okay. Watch the ruler carefully. Watch the ruler carefully when I put the ball on. What did it do? It bent a little bit, didn't it?
Drop it.
Okay.
Drop it.
Please
Drop
hold it
it.
over class, no.
Do it. Drop it.
Okay.
It's gonna break.
What's happening with the ruler?
It's bending.
It's bending. I'm not making up on it at all. Okay. So this is what's happening on a microscopic scale on the table. The material inside is bending, and there are stresses, internal stresses that are created in the material. The fibers of the wood are pulling apart, and they're tugging on each other, and they're stretching. At a molecular level, all of the magnetic bonds between the electrons and protons, okay, are being stretched. If you have enough bonds, you can hold on. If you don't have enough bonds, what's going to happen?
It's going to break.
It's going to break. So that magnetic force at the atomic level is actually acting like a spring pushing back.
Wait, how is it magnetic?
because of the electrons and protons. The bond is all magnetic, right? You have a positive and negative charge. They're attracting each other. Yes. Okay. How does the bond happen? How does the bond stand? Molecular forces. It's like a magnetic force. It's
It's
like
like
the
a magnetic.
Like
It's
a
not.
magnet.
Yeah, it's not a magnetic.
Elements are magnet.
at the same level. It's still okay. Now you're getting into tit for tat at higher level of physics. Okay, is it magnetic or is it not? It's really up for question. Right? You're calling it molecular forces. If you want to call it molecular forces, call it that. I'm gonna call it that. Now look, here's the deal. Here's the deal. At a microscopic level, when I put the bowling ball on the table is doing what? Bending slightly. Okay. When I put the billiard ball on the table, what's it doing? Bending slightly. When I put the pencil on the table, what's it doing?
Bending slightly.
Slightly. You just can't see it. It's so small. This floor, this concrete floor here, this concrete floor is designed to hold all of us, and the weight of materials, and the weight of the roof, okay, without bending too much. There is a slight bend in this floor. You have probably all felt that you've been on a bridge and a truck has rolled by and you felt that concrete move. haven't you?
Don't you like to have sensitive kids though? Like,
Depending on what you want. Some of you can't control. You have to design for it. You have to design for it. In some cases, you want it to bend because you want it to give before it breaks, right? And that's correct. But if there's a certain amount of give you don't want, right? You don't want me to walk on the floor and all of a sudden do this. Right? That's not. If I made this out of like neoprene, that would not be very helpful. But this floor will bend. On a Sunday when no one's here and I walk in here, usually I can't see the floor bend when I walk up. I haven't been in any of those before. So anyway. So the floor does bend, you just can't see it at that level. Okay? And there are at RPI, Rensselaer, years ago, they built a new library. The architect who designed it forgot to account, this is the story, they forgot to account for the weight of the books. And they started putting books on, they saw the floor deflect. And they said, hey, we need to go back and check it out. And so they had to go back and
I feel like those are bad architects.
Huh?
I feel like those are bad architects.
Those are bad architects. Bad civil engineers. Let's look at that. All right. Can you do me a favor? Yeah, where's yours? Yeah. All right, Hunter, can you go back in the back and get me a piece of wood in the bin real fast? See if I'm in here a piece of wood?
Oh, I have a piece of wood.
No, I know I'm long thing. No, right here. Hunter, right here. Next to the drawing.
I'm stepping into the
No, long thing.
I'm being quiet. Wait.
That'll work. Alright. Okay, so we've got a piece of wood here. Okay? Got a piece of wood. I can get the bonds to break. I can get the bonds to break. Where's it gonna break?
Walls.
Where the holes are. Where the holes are, because it's where the holes are. It broke where the material was thinnest. Where you have the least number of bonds. It didn't break here. You have more bonds here. You have less bonds there. Okay? Yes, get out of the way. Shoot. Shoot. Get.
Campus is not handicapped the same.
Okay. Shh. Quiet. Now listen. Guys. Shh. Quiet. Okay. So let's talk about where this goes. So every object, if I have my ruler that's bending. Woo!
I could have never thought of how to draw that.
Well, actually. Okay. So what forces do I have acting on the bowling ball hanging out the ruler? Okay, so watch what I'm doing. I'm drawing an arrow, force of gravity. Why did I draw an arrow? Because force is a vector. Force is a vector. It's an arrow. Okay? What other forces do I have acting on this?
Pushing up.
Okay, there's another force
Air resistance.
pushing up called the force of ruler. Okay? Shh. They're both the same length. They're just opposite directions. Okay?
Force of what is it called? Force of.
Force of the ruler. I could call it force of peak elephant. It doesn't matter, right? But it's a force from the ruler. I just love the childhood trauma. What? Yeah. The what now?
So there's also the force of magic.
Force of magic. The force of magic. There's always a force of magic. Okay. All right. So we've got two forces. They're equal and they're opposite. How much motion did the bowling ball have when it was resting on the 0? So what was my acceleration rate? 0. So if my acceleration rate is, and we know that the force, the total force, well, any force is equal to mass times acceleration, okay? And this acceleration goes to 0, what's my force going to go to? 0. Now, when I say force, I only have one here, don't I? But I have two. So this is really what I'm talking about is my net force. My net force is equal to my mass times my net acceleration. Because at this point I have two forces. And if my net force is 0, what does that mean about those two forces? What does it mean about those two forces? What?
Has to equal 0.
Okay, the sum of the forces, or the forces net, okay, must equal Fr plus Fg, and that sum must equal 0. Does everyone understand that? That means that Fr and Fg, if the values are the same, the values must be the same, but they must be what? Opposite. So negative Fg plus Fr, right? The reason we're doing this, guys, is that when you have an object, you're going to. Okay, Thomas, I understand you're in a wheelchair, but you've got to spin around. You've got to spin around. So I'm gonna help him spin around. Thomas, you know why you can't spin around? Because you put yourself in that position. You should have stayed where you were and not goofed around rolling back here. That's your issue. It's your fault. Okay. Shh. Thank you. Okay. Back up. Okay. We've got an object. I'm going to redraw what's called a free body diagram. We're going to draw what's called a free body diagram. Okay, it's FBD, free body diagram. For the bowling ball that's sitting at that place. Free body diagram.
No, it does not.
I haven't done it, I haven't completed it yet.
No, like the word diagram is not diagram.
So, again, I'm going to put on there my force of gravity. Oops. And my force of the ruler, right? Okay, now look, here's the thing. Because it's a vector, I can take this arrow, guys, and I can move it to here. This is just as correct as the other way. In the same fashion that I had, if you guys remember, I had velocity v, right? And we had vx and vy. Right? And we took this velocity vector and we just sort of moved it over to here, right? Okay? We can move these vectors anywhere you want. So you could put, a correct diagram is either like this. Oops. Your correct diagram can be this way. It can be like we originally had it down here. Okay? It could be here. It could be having this up here. Okay, as long as it is, all of my vectors are in the same magnitude and same direction. Okay? What I cannot do is this. I cannot write a vector like this. Is the gravity vector working on the side? Working? Okay. So we're going to be doing this as time moves on. We're going to be doing free body diagrams. We've got to figure this out because at the end of the day, all of the sum of the forces are going to equal the sum of the mass times acceleration plus the mass times acceleration plus the mass times acceleration. And then there's going to be some sort of net force at the end. Okay, and that net force is equal to our net mass times our net acceleration. Okay? And then we can start to figure what's going on. Start to figure out final movements. Because ultimately, if I have an object that is excuse me. Excuse me. Thank you. I have, let's say, a crate. Okay. Oops. And we're going to be doing this problem very soon here, guys.
That's a good box. Just like the box from
What is coming out of your
That's
mouth?
what I was thinking.
It's a rope. Okay, there's a rope. And then there's
Almost did it.
there's a rope here. Here's this force 1. Here's force 2. Okay? And
What's the end goal?
the end goal is to figure out the final motion, the final velocity, the final motion direction. Okay, so we'll be able to solve this kind of problem where we have multiple forces. And how do you break your forces down?
It's a separate mass and acceleration.
No. What is bing, 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 bing? Okay. Horizontal and vertical. They're vectors, okay? Because these two vectors are horizontal and vertical, this one is at an angle. You can break it down to horizontal and vertical and deal with them. Does the vertical force and therefore motion affect the horizontal force and their motion? No. So you got to break them down into their basic vector units. Okay. We're gonna do that. We're gonna do that next week. Deliverables. I'll give you till Sunday night for deliverables. Have a good weekend.
But let me tell you a story now.